welcome to this explainer. Today, we're diving deep into the aggressive chemistry of ammonia and exploring exactly how engineers build highly specialized systems to contain it safely. Ammonia is honestly a fascinating chemical. It's incredibly useful, but it demands serious respect and highly specific industrial designs if you want to handle it safely. So we're going to break down its physical journey through an industrial system, literally mapping out the precise materials and engineering techniques required at every single step of the way to prevent a disaster.
To really understand how to contain ammonia, we first have to understand its core behavioral quirk. You can almost think of ammonia as this thirsty, water-seeking entity. Now, in its anhydrous state, meaning completely without water or humidity, ammonia is actually considered a relatively non-corrosive, stable substance. It basically just sits there. But the exact moment it finds even a tiny trace of moisture, its personality flips completely. This water-seeking property is the fundamental challenge engineers face because, well, in the real world, moisture is everywhere.
So here is exactly how we'll construct our safe system today. First, ammonia's chemical interactions. Then, tank materials, pipeline selection, valve materials, gasket materials, and finally, safer piping methods. Okay, jumping right into Section 1, ammonia's dangerous chemical interactions, specifically the high pH threat. When anhydrous ammonia meets water, a dramatic chemical transformation occurs. It reacts, significantly increasing the concentration of hydroxide ions in the solution and becomes a strong base that's fully capable of causing severe chemical burns.
The absolutely crucial point here is that this reaction with water raises the pH level dramatically. Pure water has a neutral pH of 7, right? Well, the presence of ammonia spikes the pH of that water to greater than 11. This creates a highly corrosive, strong alkaline threat that will easily eat right through standard industrial materials, plus it becomes an alkaline-reducing agent, meaning it reacts dangerously with things like chlorine, fluorine, bromine, mercury, and hypochlorite. That number, 11, is the primary reason why your standard plumbing and storage solutions are completely off the table.
This perfectly illustrates the varying threat levels. Notice how, in the presence of moisture, ammonia reacts with and actually corrodes metals like copper, brass, zinc, and their alloys, leaving behind this distinct, messy, greenish-blue residue. But it's not just about corrosion. We have to talk about heat. When ammonia reacts with water, the process is highly exothermic. It violently increases the temperature of the water. And this temperature spike actually favors the reverse reaction, the undissociation of ammonium hydroxide. That means the ammonia becomes less soluble and can be dangerously regenerated from the water solution. This specific property of heat generation and solubility reduction is a massive critical factor right now for the maritime industry, especially as ships increasingly look towards using ammonia as a future fuel.
Let's move on to Section 2, storing safely, and our first line of defense, the tanks. We'll see how our engineering solutions build up, starting right at the origin point, where the storage tank acts as our very first mechanical defender against this chemical.
Because ammonia is often stored at extremely low temperatures just to keep it in a liquid state, standard steel simply gets way too brittle and dangerous. You just can't use it. Instead, engineers rely on heavy-duty FH36 steel. This specific grade of steel is specially rated for low temperatures and possesses remarkably high impact toughness. It's designed precisely to handle extreme physical and thermal stress safely, ensuring that our massive reserves of liquid ammonia stay securely isolated from the outside environment.
All right, Section 3, transporting or forging the pipeline. Now that we've safely contained the ammonia in our FH36 steel tanks, we have to safely transport this volatile water seeker throughout the facility. To pull this off, we forge the very arteries of our system out of a highly specific material, high-pressure specification stainless steel, specifically SUS 316L. Remember how copper, brass, and zinc corrode into that greenish-blue mess with just a drop of moisture? Well, SUS 316L is chosen for its rugged durability and total immunity to that specific alkaline attack. And it's forged to a high-pressure specification because an ammonia system is constantly under immense internal forces. The pipeline literally must never bulge or stress under that load.
Section 4, controlling flow at the valve checkpoint. As the pressurized ammonia raises through those stainless steel pipes, it inevitably reaches the valves. These are the mechanical gates that control the flow, stopping and starting the pressurized liquid on demand. What's really interesting here is the specific metallurgical recipe required for these mechanical gates. The valve body isn't just standard metal. It's made of cast stainless steel for extreme durability. But engineers take it a step further. They add specific amounts of molybdenum and chromium directly into the metal alloy. This targeted addition massively boosts the valve's overall corrosion resistance, guaranteeing that the internal moving parts don't degrade over time when exposed to that intense, high pH ammonia environment.
Moving to Section 5, sealing tight, it's time for the gasket showdown. We've got the tanks, the pipes, and the valves, but wherever two pieces of metal meet, you naturally have a joint. To prevent our alkaline-reducing agent from escaping at these joints, we need highly specialized seals.
When you're designing these systems, you'll find ammonia's compatibility with elastomers, the rubbery materials used for seals, varies wildly. On the recommended side, we have our reliable defenders. Teflon and graphite are universally excellent. Certain elastomers are also found within strict temperature ranges, like neoprene between -40 and 80 degrees Celsius and butyl between -54 and 149 degrees Celsius. But seriously, look at the do not use list. Contact with natural rubber, nitrile, polyurethane, or Viton is strictly a no-go, especially at low temperatures. If you try to use natural rubber or polyurethane, the cold ammonia will completely destroy the structural integrity of the seal, and that leads directly to a catastrophic leak.
For the ultimate tight, fail-proof seal in our high-pressure flanges and valve stems, engineers don't just slap in a simple flat piece of rubber. No way. They use spiral-wound graphite gaskets reinforced on a metal backing. And for delicate moving parts, like valve shaft stem seals and glands, they utilize pure graphite paired with EPDM O-rings. This specific combination creates an incredibly tight, reliable seal that is completely immune to the chemical degradation ammonia causes in standard materials.
Which brings us to Section 6, methods for safer piping and optimizing the system. We have all of our physical materials perfectly selected, but material science alone isn't quite enough. How do we structurally and chemically optimize the entire piping system for maximum long-term safety? Well, to make sure our SUS 316L pipes are truly ready, we utilize a bit of chemical wizardry called passivation. This is a targeted chemical treatment applied directly to the stainless steel pipes well before the ammonia is ever introduced. It deliberately increases the surface's natural corrosion resistance to an extraordinary degree. Let's walk through exactly how this brilliant process works, step by step. First, the interior of the pipe is circulated with, or immersed in, a nitric or citric acid solution. This acid actively dissolves any microscopic, vulnerable free iron lingering on the surface, but it importantly leaves the stronger base metal completely intact. Next, the acid is thoroughly rinsed out to neutralize the surface, and the pipe is dried. Finally, here's the magic moment. When that freshly exposed, iron-depleted surface meets normal oxygen in the air, the chromium that's naturally present in the steel reacts to form an incredibly thin, we're talking just 1 to 3 nanometers thick, impenetrable chromium oxide passive layer. This microscopic shield is basically the ultimate armor against ammonia.
But even with perfect materials and perfectly passivated pipes, human error and mechanical wear are always going to be factors. So, the ultimate structural question is, how do we stop leaks before they even have a chance to start?
Honestly, the absolute best defense is simply removing the opportunity for leaks entirely. In a state-of-the-art ammonia system, engineers will just weld the majority of the pipeline directly together. By physically fusing the metal, you completely eliminate the mechanical joints that have to rely on gaskets. We minimize open joints wherever physically possible. Flanges, those bolted, gasketed connections, are strictly restricted only to areas where small instrumentation has to be removed for maintenance or calibration. Every removed flange is a removed risk. It's as simple as that. So, what does this all mean for us? Ammonia is a powerful, demanding chemical that plays by its own strict rules. It seeks water, it dramatically spikes the pH, and it will destroy unprepared metals and elastomers. But as we've seen today, with precisely selected FH36 steel, passivated SUS 316L pipelines, molybdenum-reinforced valves, and specialized graphite seals, it absolutely can be contained. As global industries, especially the maritime sector, rapidly turn to ammonia as a zero-carbon future fuel, the stakes for getting this engineering right have literally never been higher. Which leaves us with one final thought to consider. As this transition accelerates, is your facility's metallurgy truly prepared to tame the water seeker? Thank you so much for joining me for this explainer.